I'm having one doubt. Can I ask right now or after some time?
Go ahead. If it's possible to answer, I'll do that. Otherwise, we can take it up later. Go ahead.
Okay. Sir, in the slides of lecture number 16,
Mhm.
while solving the Bode plot of the transfer function in which you had just a minute. Can I share my screen, sir?
Uh, uh, I'll open it. Okay.
Yeah, you
And
open it, please.
I'll do that. So, lecture 16, right?
16, yes.
Which slide?
Slide number 13.
13. Yes.
Sir, in that, when we are just decreasing, when we are going from 100 to 1000 omega, at
100
that
to
1000,
uh-huh.
in that, sir,
Oh,
how can the slope be minus 20? It should be minus 40, right? Because both are decreasing.
which graph are you looking at? The red one?
Yes, sir.
No. So see, j omega, the first one, j omega 1, is giving rise to a positive plus 20, right?
Yes.
Then this one will give rise to a minus 20. So they cancel
Right.
together so that you get 0 dB,
Yes.
right? And then this one comes into picture, so that adds a minus 20 dB.
Sir, but in that the upper one is gone, no? Or else it will be there.
No, no, the two of, see, beyond 100 hertz, these two, j omega and 10 plus j omega, they cancel each other,
Right.
right? Their effects are nullified. So you're only left with this last term. That will only give you minus 20 dB.
No, sir, I'm saying after 100, after 100, the one which is having positive slope is out of question of j omega. Or is
Both
it
this
there?
one plus this one. Both the, let me see, just a second. Both this term, the second term and the third term both go away. They are canceling each other, second and the third term.
Okay.
And so you're left with only the last term. The last term is minus 20 dB per decade.
Okay.
Right? So don't forget the j omega and then 1 plus j omega by 10. All right. So please, everybody on mute. Everybody on mute. So let me come back to, I think the reason why I was delaying the homework 4 solution was I thought I'll, normally these things are covered in tutorials, so I thought I'll cover it today. So I will do it quickly. Homework 4 solution. Let me see if it's being recorded or not. Yeah, it's being recorded, so that's fine. So homework 4 solution, we'll quickly go over it. Anytime you have any issues, please stop me and we can discuss. And then after that, we'll take up the problems, other problems that you may have. Also remember 6:45 is we'll start our tutorial quiz. But aside from today's discussion, I think many people have posted some queries. So I'll take it up and answer it in a separate video if required and post it for you guys. So homework 4 solution, question number 1. What you are asked to do is, this is a series LCR circuit, and you're asked to basically determine the time at which the output voltage V0 will settle to within 5% of its final value. So these are basically simple questions, just so that when you answer them, it will help you absorb the concepts that have been discussed in the literature, in the lecture. So omega naught, the standard expressions are there for omega naught in Q. The fact that Q is greater than 0.5 means that it will exhibit a oscillatory behavior. Output voltage will not reach its final state in a monotonic manner here. This is the frequency, but the frequency with which the circuit will oscillate is this one. Omega 1 is omega naught, square root 1 minus 1 by 4 Q square. Normally Q is large, and therefore omega 1 is practically equal to omega naught. But if one wants to be more accurate, you can see the difference, 3.16 here and 3.12 here. Shashwat, yes, go ahead. Shashwat, you have a question?
Sorry, sir, it was a mistake.
So
I'm
if
extremely
not,
sorry. Sorry, sir.
Okay. So the capacitor voltage, when it's in this form here, oscillatory form, the capacitor voltage is given by the steady state value. So there is a correction here. This should be 5. There's a correction. VCT is equal to 5 here, and then there is this part here, oscillatory part here. And note that the oscillatory part that is there here is decreasing at the rate of e to the power minus r by 2lt. So e to the power minus t by tau, tau is 2l by r, which turns out to be 2 milliseconds. And we've asked how much time will it take for it to settle within 5%. So recall that 5% is 5%, or when the output reaches 95% of its final value, these are like 3 taus. So you have to wait for 3 time constants. So 3 time constant means 6 milliseconds. So you have to wait for about 6 milliseconds for this term to reduce to within 5% of the final value here. And indeed, if you look at the simulation results here, when I go to 6 milliseconds, my output is 4.77. It's not exactly positioned at that point at 6. So 5% means the output is 4.75. So it's close to that. 6 millisecond is the answer that is there here. So the output is, if I look at the peak here and the peak here and the peak here and start looking at it, the rate at which is decaying at a rate exponentially with a time constant of 2 times L by R. So these are all equations are all in the notes. It's a question of basically plugging in numbers and applying the concepts. So as I said, I'll go over it quickly. The second one is the switch is opened and another resistor is provided a path, and what you're asked to sketch is the qualitative variation of current and capacitance voltage here. So whenever you are asked for a sketch, qualitative sketch, the first thing you should do is calculate the Q factor. And if the Q in this case is greater than 0.5, then there would be an oscillatory behavior, otherwise monotonically decreasing thing here. So omega naught we calculate, and the first thing you calculate is omega naught, then you calculate Q. And in this case, you would of course find Q is greater than 0.5. But in general, R has to be less than 316 ohms for Q to be greater than 0.5. So that tells us that R2 has to be less than this. Anyway, so that was the quiz problem also. So note the variation. The capacitance is all charged up. So the capacitance will, of course, the red one is the capacitance voltage here. So it starts off from a value of 5 and it has to discharge. And of course, because Q is greater than 0.5, it doesn't monotonically decrease to 0. There is an undershoot and overshoot and kind of a thing. And then it settles down. So that's the nature of the capacitance. And the inductor current, of course, inductor will not allow current to immediately increase. So inductor current is in green. Green is this axis here. So inductor current starts with 0. And then the current builds up. And then, of course, it also undergoes this oscillatory behavior. And of course, eventually the capacitor is fully discharged. So the inductor current also settles down to a 0 value here. All right, so that's the, we have discussed these things in more detail in the lecture also. The third part was a parallel LCR circuit, and the question was, sketch and explain the qualitative variation of current and the capacitor voltage in the parallel LCR circuit. So in this case also, if we were to calculate omega naught and Q, we'll find that Q is such that you'll get oscillatory behavior here. And so if you close the switch, of course, final value is, the steady state value is that the inductor would be a short and the current in the inductor would be 10 divided by 500, which is 20 milliamperes here. So we focus on the green curve, 20 milliamperes is the inductor current. So the final value, of course, is 20 milliamperes here. But the inductor current doesn't, again, monotonically go there. It exhibits a oscillatory behavior here. And the capacitance voltage also exhibits a behavior like this. So I'll leave it for you to think about at this stage why there is a lag between the two. Why the inductor current is lagging behind the capacitor voltage, and what happens at the peak value, what happens when the inductor current reaches a zero value. So think about the state of the circuit. We've discussed some of these things in the lectures, but go over it in the context of the problem that is given here. See what happens at each individual time, the peak of the voltage here, or the peak of the current here, the zero current here, the negative peak here, what exactly is happening here. All right, so go over it, make sure you understand the details of what happens in the circuit. All right, so let's come to question number 4. So question number 4 is we need to analyze the circuit using the method of phases for the value that is given here. And the first thing that we do here is identify omega. And then we draw a phasor circuit. So we convert each one of them into their reactance values or impedance values here, right? So each one of them is converted there. And then the phasor circuit is over here. And the input is also converted into a phasor value 5 angle 0 here. So now is the usual analysis. We are asked to calculate the output voltage. So what I'm trying to do is calculate the net impedance due to this particular part here. And the impedances are easy to calculate, J10 and minus J20. So it becomes minus J10 here. The two add up to give a minus J10, and minus J10 in parallel will give you minus J5 plus J5. So it all adds up to 0. So this whole thing, so which means that the circuit is in a kind of a resonance state. All the imaginary part of the circuit is imaginary impedance is going to 0 here. So that makes it simple. The current then is simply 5 by 50. And so 0.1 angle 0 here. Now, of course, we have to find the output voltage here. So this current, once we have calculated, we would eventually like to calculate what is the current in this branch multiplied by the impedance here and calculate the output voltage. So that's what we are going to do. I1 is what we are looking for. So I1 will be, note that J10 and minus J20 is minus J10. So it's a 2 branches, both of them same impedance. So the current divides equally between the two. So it's easy to write down, is 0.1 by 2. And then the output voltage will be simply I1 multiplied by minus J20. So we get an output voltage here. All right. And then once you get an output voltage here, of course, you can convert it back into your time domain as a cosine with a proper, so it's cosine 100t and the phase value put in over there. And you get the final value. All right. So that's the procedure that we follow in all of them here. So this part was, this is a source of slight discomfort to many people. So a student applied, so this was a real case in one of the ESC201 laboratory. The students were working with LCR circuit and the student was claiming that he has applied 10 volts and he was getting very high voltage here across the 10 microfarad capacitor and was wondering if there's something wrong with the circuit, something wrong with the measurement. And so it's around, because normally when we handle resistive circuits, we know that you have a supply voltage and then there would be drop across various elements. And therefore, any voltage across any element is less than the supply voltage. So when we handle resistive cases, that's the notion that we carry, that voltage across any element would be less than the supply voltage. But then when you come to these AC circuits with these impedances, interesting things happen that that rule is no longer valid. The expectation that the voltage will always be less than the supply voltage is not really true, but it's a useful result. So let's look at it. So we convert it into j omega L and minus j 10 to the power 3. So frequency is given, so we convert it into the values that we are given here. And we are also given 100 volt sine 100t. So remember, we are casting everything in the form of a cosine. So that becomes 100 angle minus 90 here, the voltage at this phase here. So V naught we can write according to the voltage division that we have, minus j 10 to the power 3 and all that you see here. And note that the output is 90 degree out of phase here. So 90 degree out of phase with the input that you see here. So it's obvious that what is happening is that this imaginary term is going to 0. If I make this imaginary term equal to 0, I'll be left with only a j, which is same as minus 90, and the equation would be satisfied. So if we put it equal to 0 here, we get a value of 10 henries. So the point is, if I put 10 henries here, the reactance of inductance and reactance of capacitance are canceling each other. Then my output is simply minus j 10 to the power 3 by r equal to minus 10j. And if I choose r equal to 100 ohms, I will get 100 volts here. Right? So in a series resistive circuit, one would expect voltage across a resistor to be less than. However, because there's a cancellation of terms here, cancellation of impedances, this is no longer true. And voltage across an element can be much larger than the source voltage itself. Anyway, so we've seen examples of this in other contexts also. So, but of course, this is, please do not think that you've built an amplifier by this means, that you've applied a 10 volt and you're getting 100 volt. This is not an amplifier. The essential condition for amplification is that you should get power gain. There's no power over here. And if you try to extract power by connecting a resistor, let's say across it, you can verify that you will not be able to get a power gain through a circuit like this. So to call something an amplifier requires that there has to be a power gain. And this can never happen in a passive circuit like this. So connect a resistor here and try and see that can you connect any resistor and get a power across that particular resistor, power dissipation. So you have 100 volts here. You might think that if I connect a resistor here and so 100 volt, and I may get a lot of power dissipation in that particular resistor. So try it out and convince yourself that you will not get power dissipated in this more than the power that you're sending from the input. Related to that is the parallel LCR circuit. So parallel LCR circuit, we have determined suitable value of inductance such that output voltage V0 is maximum. And this is one element, and you can combine the LC into another element, and let's say the equivalent impedance is Z equivalent here. So we can write this out. And note that voltage is a division between this and this here, this particular part here. So V0 is Z equivalent by Z equivalent plus 100 times Vs. And to obtain maximum output voltage, according to this expression, Z equivalent should be as high as possible. Then V0 will be practically equal to Vs. And one can see that Z equivalent, we can actually get infinity. We can do a cancellation if we choose L properly. C is given, so if we choose L properly, we'll get a cancellation here. We'll get an infinite value of Z equivalent. And so L equal to 10 Henry will give that. And then V0 is practically equal to Vs. This part of the circuit acts like an open circuit. Now, this also brings in an interesting thing, that if this is an open circuit, L and C are canceling each other. The reactance is open circuit. So obviously the current drawn from the supply is 0. So no current is being drawn. And we are saying that V0 is Vs, so drop across 100 ohm is 0. But that doesn't mean, so normally one would expect if the current coming in from here is 0 here, then and then you would say, well, the current then divides between 10 microfarad and L here, and if 0 current is entering, then 0 current should be here and here, but that's not true. So IR is 0, but IL we can calculate because we have a value of V0 and we have a value of impedance. So we can calculate. There's a fairly large current here, 0.01, 10 milliamperes here, and an equal amount of current flows through this other part here, through the capacitor also, 10 milliamperes here. Of course, the two currents are opposite in phase and they're canceling each other, right? So one can have substantial current here, but no current here, right? So again, this notion of current division that we have, that a current comes in and it divides between two currents, and the currents into which it divides are necessarily less than this original current. All of that fails here. When you have negative values of impedances and positive values of impedances, things can cancel each other and result in 0 current, but current here and current here. Of course, there's no violation anywhere in KCL or KVL or any of those things, except that the notion that we carry because of our earlier exposure to resistive circuits, and when we come here, our earlier notions of voltage division and current division, they interfere with these new things that we see here, right? Okay. All right, so that's question number 6. Okay, so that's IR is 0, IC and IL are non-zero. Question number 7. In the circuit shown below, we have, it's like the 2 radio channels, let's say, channel 1, characterized by 1001 megahertz, and another channel located very close, F2 at 1.1 megahertz. And we would like to receive this channel 1, and channel 2 we would like to reject, right? So our interest is in that. And so we selecting one channel, radio channels or television channels, is often done through these LC circuits that you see here. So what we want is a kind of a design in order to accept channel 1 and channel 2 we would like to reject. So note that when you are exciting a circuit with 2 different sinusoids of 2 different frequencies, so when you convert into a phasor circuit, there would be 2 different phasor circuits. When you are looking at VS1 with frequency of 1 megahertz, then of course you'll use omega 1 and you'll calculate the impedance of capacitance and inductance according to omega 1. When you're looking at VS2, then you'll calculate according to omega 2. So whenever you have signals of more than one frequency, you will have to analyze it using superposition. First with source of one particular frequency, and then with the source of the second frequency, and then add up the results. So that's how you need to do. If both of them happen to be of same frequency, then of course single circuit can be done, and you can do it through one analysis. Okay, so superposition is required. Since we would like to listen to channel number 1, of course, we would like to maximize the output voltage due to VS1. So we just saw a problem in which you want to maximize the effect of VS1, which means V0 making practically equal to VS1. We saw that maybe you should cancel the effects of inductance and capacitance at that particular point here. Okay, so let's look at this one. This is Z equivalent. Z equivalent plus Z equivalent plus R, V01, VS1 here. Z equivalent is this parallel combination here. We should maximize Z equivalent. And so J omega L1 and 1 over J omega 1C is a parallel combination of this. So if you want maximum value of Z equivalent, make this part as large as possible. Make this term equal to 0. And that tells us how to choose L and C here. Okay. So we obtain L and C here, and note that this part goes to infinity, and therefore my circuit is simply a voltage divider between this R and this R. These two cancel each other, and we obtain V01 is 0.5 VS1. So that's for VS1. provided we choose C equal to 25.33 PF here. Now we want power due to VS2 to be less by a factor of 1000, right? Is it given in the problem? By a factor of 1000, okay. So by a factor of 1000, so power by a factor of 1000, which means VS2 should be less by square root of 1000, right? So because power is square of the voltage here, so you want V02 to be Vs1 by square root of 1000, which is 63.24. And therefore, Vs2 multiplied by Z equivalent 2. Now, Z equivalent 2 is this. We have already chosen the value of C. So this whole thing evaluated at omega 2. And Z equivalent 2 plus R should be Vs1 by 63.24 here. Z equivalent 2 is over here. And so let's come over here. So since this factor is, so we can get, we're getting a value of R. R is 63.24, Z equivalent to here. See, basically from this equation. And so R is this one here. Z equivalent to is R parallel of this. So we can get now the final value of Z equivalent here. And, we can evaluate what is the value of R that is required. Okay. So basically, once you have that using those equations, the value of R that is required is 2 mega ohms to obtain a circuit which will accept 1 megahertz signal and reject the 1.1 megahertz signal by a factor of 1000. And if your interest is in accepting 1.1 megahertz, then you can change the capacitance and tune the circuit so that it gives a peak at 1.1 megahertz, and then it will reject the 1 megahertz signal. So that is what is happening in radios and TVs. Some L and some C is being changed in order to select a particular radio channel or a television channel. And these are calculations which tell you how you can do those things that are there. Let me keep tab on the timing here. Okay. Use Thevenin's theorem. So we said that once you convert it into a phasor circuit, your Thevenin superposition, source transformation, all of those things are valid. Okay, maximum power transfer, except that remember in the simple case, maximum power transfer occurred when RL was equal to the Thevenin's resistance. In this case, ZL has to be equal to complex conjugate of the Thevenin's resistance. So that's the change that one has to do. To get maximum power dissipation, a result which was discussed in the lecture. Okay, so use Thevenin's theorem to determine ZL such that maximum power, so fine. So to determine Thevenin's resistance, let's open up the current source here, open up the current source, let's short the voltage source here. And since there are no dependent sources here, so note that when there are no dependent sources, you can remove independent voltage and current sources, and then it becomes straightforward to calculate what is the net impedance between those two terminals here. So this is open circuit. So basically these two add up, and Thevenin's resistance becomes the addition of these two. So this is 4 angle 45. There's no need to do maybe open circuit, short circuit here because calculation of resistance is straightforward. So maximum power will be dissipated, choose ZL to be complex conjugate of this. So 2.82 minus J2.82. So that's, once you do that, so that is straightforward. The other thing that we are asking is determine also the power dissipated in ZL and power supplied by each one of those sources and all that. So we need to move forward and calculate for the Thevenin's voltage also. So since we've already calculated the Thevenin's resistance, we can also calculate the Thevenin's voltage by calculating the short circuit current. Yeah, Aditya. Aditya has a question?
No, sir, it was by mistake.
All right, okay. Okay, so let's find the short circuit current. So we short these two, and then the short circuit current becomes straightforward. This 5 angle 45 will obviously flow here. and then the current from this side will come and flow into this short circuit here. So that current is simply this voltage divided by the net impedance here. So concept-wise, it's simple, except that handling complex numbers will require some more effort. So please be prepared in the mid-sem when it happens with your calculators, and so those would be necessary. Anyway, so ISC is here, and VT Thevenin's voltage multiplied by Thevenin's resistance, and you get the value of the Thevenin's voltage here. And so Thevenin's equivalent circuit then becomes the Thevenin voltage here, 40 angle 90, ZT Thevenin's resistance here, which we have calculated earlier. And we have chosen ZL to match with ZT to get maximum power dissipation here. So now we can calculate what is the net load current here by simply simple KVL. And note that we have a value of ZL which is given. So this is the IL which is flowing through this particular, in the series circuit here. That's the IL. So our strategy is, when you have a simple circuit like this, our strategy is to find the magnitude of the current that is flowing here and look at the resistive part of the impedance here. And basically power dissipated would be I square RL. Remember, there's no power dissipated in the reactive part here, either the inductance or the capacitance here. So that's why we are finding IL, and we'll focus on the magnitude part of this. And when we have a ZL, is the resistive part of ZL, or the real part of ZL will be RL, will be 4 cos of this, 4 square root 2. And power dissipated would be the magnitude part of it, I square times RL divided by 2 here. Okay, so power dissipated is I square RL by 2, and so that is 70.1 watt here. Okay, so that's the power dissipated in the load here. But we also have to find out what is the power drawn from here and what is the power drawn from here. All right, so let's proceed with that. So Thevenin's equivalent will not directly give us, see, there is no source here now. The source is gone. This is Thevenin's voltage here, and this is Thevenin's resistance here. So it helps us to calculate what is happening in the load, but we have to go back to the original circuit to find out what is the power drawn from this supply and from this supply. We have to find out the net voltage here and the net current flowing from here. So we have to go back and then look at it. Okay, so we are back to this circuit here, and we know, of course, this one here. So using Thevenin's equivalent circuit, we can also find out what is the net voltage across ZL. Right, Thevenin's will also give us the net voltage across ZL. So the idea is that once I get this voltage here, the voltage across ZL, and then I already know this is 5 here. So I already know what is the power dissipated in 100 ohm resistor. Basically 5 square multiplied by 100 divided by 2. So I know the power dissipated here. So what I'm trying to do is, if I can find out the net voltage across ZL, which is nothing but the net voltage across the combination, and I know the current flowing here, so I can find out what is the net power which is drawn from the combination of these two. And then from this combination, I'll subtract the power dissipated in 100 ohms and get the power drawn from here. So that's the strategy. So because VL I can calculate very easily. And so the power drawn from the combination of the two would be the net voltage. Note we are doing RMS, so 20 square root 2 is square root 2. So the RMS value here. The net current, which is the RMS value 5 by square root 2. And the angle between the two of them, between the voltage and the current, cos of the, so that's called the power factor. So the current is 5 angle 45. The voltage is also angle 45. So the net angle between voltage and current, net phase difference between voltage and current is 0. That's why we put cos of 0 here. So the power which is drawn from, note that it is negative because the current is flowing out and the voltage is positive here. So the power which is drawn from the combination of these two is minus 70.11 watt. And we want the power drawn only from here. So we have to subtract the extra power which is dissipated here. So from minus 70.11, we subtract the power dissipated in 100 ohms, and we get the sum of the two, which is the 2 here. So that's the power which is taken from here. Okay, note that it is negative, supplying power here. So power dissipate is positive, power dissipate is negative. Now the point is, note that you can do a problem, any of these problems, in many other ways also. I'm just highlighting one particular way because we already have a Thevenin's equivalent, so we have VL available to us. And because we have VL available to us and we already know the current here, so the power from the combination can be easily calculated, and then power dissipated in the resistor can easily be calculated. Therefore, the power from this particular source becomes easy to calculate. Coming back to the power from the other source. So power from here, we have to calculate this current IS because the voltage is known. And again, we know VL. We've already calculated VL. And therefore, the current that is here would be simply this voltage minus VL divided by the net impedance between here. So that's what we are doing to calculate IS. And so this is the value of IS here. And then power will be the RMS value of the voltage here, 20 by square root 2, the RMS of the current, so 5 by square root 2, and the angle between the voltage and the current, so 90 here, and the current is 135. So the angle is difference, the phase difference is 45, cos of 45, and then combine them together. So get the power which is drawn from here. Okay, so that's a little bit elaborate. These calculations can become messy in the exams. What we'll try and do it is, as much as possible, the numbers would be such that you'll get, you know, a 45 or a 60 or a 30, that kind of an easy calculation. Hopefully, will be easier. Okay, so last problem. For the circuit shown below, determine the power factor for the power supplied by the input. And so these are, suppose this is a part of a house. Let's say these are, this could be a fan, it could be a fridge, it could be a bulb. So there are various things that are there in a house, and the power is being consumed. And one is asking how much is, you know, the power factor that is there here. And the reason why we are focusing on the power factor, just for the sake of discussion, just imagine that you had in the house, you had just an inductor, right? So assume that this is 0 and this is 0, and there is no, this particular resistor is not there. And so you have only an inductor inside the house. Now, if there is only an inductor in the house, you know, you have a giant inductor, and of course there is a voltage and there is a current flowing. But what is the power factor? Because you have only inductor, so the current is and the voltage are angle is 90 degree. Power factor is cos of 90 is 0. So you have a giant inductor inside your home, drawing a lot of current, let's say, and but you're not paying anything for it, right? Because power consumed is 0. You pay for the power consumed. So the issue is, should you be charged for drawing so much current? Because note that the power station has to supply current. And here is where it becomes important, why we are focusing on power factor. So 90 degree power factor is 0, but current is being drawn from the supply. And note that the power station may be located hundreds or thousands of kilometers away. So there is a large current which is flowing in the power lines, which have a resistance. So there is a power dissipated in the transmission lines. So even though you may not be consuming it, power is not dissipated there, but you're drawing current. You're drawing current, and that current leads to losses in the transmission part here. And therefore, it's not a wise thing to have a power factor which is very, very small, because you're not consuming anything, but you're drawing a lot of current, and that's a waste. So that's why what we are trying to do is calculate the power factor. And also you will find, if you do the calculation, I think we're running out of time. We have a quiz at around 6:45 anyway. So let's quickly do that. So basically, let's look at the current that is flowing in each one of those branches. IL1, IL2, IL3 here. IL1 is straightforward. IL2 will require a little bit of more calculation. Anyway, so 8 angle this and IL2 is here. Let's sum up all the currents. And the final answer is 22.38 minus 30.55. And so power factor, the difference between angle between the voltage and the current is 30.55 here. And cos of 30.55 is 0.86. So ideally, I would like power factor to be 1. So this angle to be 0. And therefore, because these have all inductive components here, if we add a capacitor here, this capacitor would draw some current, and but its phase would be opposite to that, and a cancellation can occur such that I can have 0 angle between current and voltage here. So that's what we are requiring. And so in this case, now we have ICs, all these things that are there here. And this is the current that is drawn in the capacitor here, 311 omega C angle 90 here. And what we are wanting is the two of them to give rise to a power factor of 1, or the phase of the current should be 0 here. So basically, we should choose omega C, the value of C such here, such that when I take 22.38 sine of 30, that should cancel with this particular value here. The imaginary part here and the imaginary part here should cancel together. So we find that C equal to 0.116 millifarad if I add to my circuit. Then what will happen is the power factor will go to unity, and I'm unnecessarily maybe not drawing too much current and causing transmission losses here. So the net value of supply current, note that if you calculate the current, is 19.27 amperes here, as compared to earlier value of 22.38 amperes here. So therefore, losses in transmission wires will be less here. You are consuming still the same power. The power which is dissipated here, the power which is dissipated here, and power dissipated here, they remain the same, because all these things are in parallel. You're consuming the same amount of power, but from the supply, from the power station, you're only demanding 19.27 amperes here, instead of earlier 22.38. And therefore, you're not causing wastage of power in the transmission lines here. All right, so that, unfortunately, that took up a lot of time, 6:42. So any quick questions?
Sir, there is no quiz visible on the Hello IITK portal.
Well, I have to go and make it visible now.
Oh. And sir,
okay, so I have to do that.
And one more
Yes?
question, sir. So in the discussion or quizzes, whenever I click for the answers, it shows that the answer will be uploaded at the end of the section, but like still none of the answers are visible.
Okay, so the reason why immediately we don't upload the answer,
no sir,
is if you click if you submit your answer, and then it will show the correct answer, which I don't want.
No sir.
So it is delayed, but I have to check what was the time put for that.
No, like for the quiz.
When will the answers be revealed?
For the discussion quiz one, the one which did in the starting, the answer for that even is not visible to me. I don't know, it's a problem.
Okay, I have to check that. Yeah. Okay, so I'll make sure that each one of those quizzes that have been held, the solution is there on the booklet. Okay.
Thank you.
All right. Any other quick questions?
Sir, please upload the solution of homework 4 and homework 5.
This is homework 4. And I was not uploading because I wanted to discuss it in the tutorial. So it's recorded. I'll upload it immediately. Okay. Homework 5, I will still give you some time to try it out. And I'll upload it, let's say, maybe 3-4 days before the final, before the midterm exam. I'll give you time to try it out by yourself. And I'll make a video of homework 5 also, the solution, and I'll explain the solution. Okay, so let's stop here. 6:44. I have to upload the quiz also. And so let's go on with that.